And Professor Gans' research focuses on service operations, including the management of telephone call centers. Professor Gans has also been the department editor of the stochastic models and simulation for management science, and also was the president of Manufacturing and Service Operations Management Society. So Noah's research has really made a great impact both in industry and also in the academic world, inspiring a lot of researchers, including myself. So without further ado, let's welcome Professor Noah Gans to give us this seminar talk. So Noah,
great. Well, thank you very, very much, Jayu and Paul, for inviting me and being patient when I didn't show up last spring. And thanks actually for everybody who had the chance. I had the chance to meet with today. That was great. I enjoyed it, and thank you all for coming to the seminar. Today I'm going to talk about airline and other kinds, but most of the example I'll be using is airline overbooking when the disutility of being bumped affects the demand distribution. And this is joint work with Rowena Gand, who is, she was a PhD student in my department. She's now at the SMU Cox School of Business, and Jerry Tsoukalos, who's a colleague of mine at Wharton. And here's an overview of what we're going to do. I want to point out actually that I told you, I've been rehearsing my slides, and I realized that I'm afraid I'm going to run long. So what I'm going to try to do is kind of burn through the introduction fairly quickly. If you have questions and are confused, you should definitely stop me, because, you know, obviously if you're confused, then you're not going to follow the rest, and it's going to be a super annoying talk. And what I'll probably end up doing is I have some numerical tests and examples towards the end, and if I don't have time, and I probably won't, then I'll give you a little foreshadowing of it. So here's the overall story. I'm going to start out with a little background motivation for the problem, a little lit review, and then I'm going to get into the main part of the talk, which is I'll formulate a model of overbooking with endogenous demand, and then I'm going to analyze it three different ways. The first way I'll analyze it is, in a certain sense, the traditional OR way, where it's really, you're just fooling with the booking limit. You're not worrying about the price or the bumping compensation. Those are given to you. And the really traditional way is assuming that the demand distribution is exogenously defined. So even with this simple version of the problem, I'll compare exogenously defined demand distribution and endogenous demand. And then I'll look more broadly at the full problem, where the airline actually has three different controls available to it. It has the price of the ticket, it's got the booking limit that it sets, and it also can control the bumping compensation. If it bumps somebody, how much it pays the people who are being bumped. And here, the bumping compensation, I'm going to assume it's a fixed quantity. It's the same for all of the customers who are being bumped. The next thing I'm going to get to is auction-based bumping compensation. And this was really the initial impetus for analyzing the problem. But we realized as a baseline, it was important to understand kind of how the problem worked in kind of simpler levels. And so I'll compare auction-based bumping compensation to fixed bumping compensation. And finally, if I have time, but I probably won't, I'll get to numerical examples, but I'll give you a little foreshadowing of what the numerical results say. So that's it. So let me get started. About 3 years ago, when we started working on the problem, there was this incident that probably many of you remember. There's a doctor who was trying to get on a flight in Chicago to get back to his patients in Kentucky. And he got forcibly pulled from the flight. And I think they punched him, and they broke some of his teeth, and he sued them. And that's not what I'm going to talk about. But what it did is it raised people's awareness about the problems of overbooking, which actually happens every every few years. And this is just one of the articles that came out at the time. One of the things that the Financial Times looked at is that, well, just how big a problem is overbooking on airlines? Down here, you can see it's talking about the quote, United Continental Furor. That's the story about this guy who got dragged off the flight. And if you look, you can see that actually the overall amount of overbooking is something under 1/10 of 1%. So in terms of percentage terms, it's actually a very, very small fraction of the people who actually get bumped from flights. Down here, there's involuntary. That's like this guy who got pulled from the flight even though he didn't want to get off. Although generally they don't beat people up. But the vast majority of people who get bumped actually will voluntarily get off the flight. So one question to ask is, well, given that the bumping rates are so low, does it really make a difference anyway? And the answer is, of course, yes. Otherwise, I wouldn't be talking about it today, right? And just so you know where these bumping statistics come from, it comes from, you can see down here, it says the BTS, the Bureau of Transportation Statistics. And here's the statistics, for example, for Delta Airlines for 2017. So that's the year that the Financial Times is talking about. And the way that you calculate it is and plane passengers, those are actually the people who got to fly. And then there are two different kinds of people who are denied boarding. There are people who are voluntarily bumped, and there are people who are involuntarily bumped. So if you add the three of them up, that's the denominator. And then if you take voluntarily plus involuntarily bumped, that's the numerator. And that fraction is the fraction of customers who are bumped. So it's about, in this case, in fact, the delta matches the industry as a whole. It's about 1/10 of 1%. And one thing I want to point out is that for those of you who know inventory theory, this is an analog of the ex post fill rate kind of statistic. And I'll come back to that in a moment. So that's where it comes from. You can see there's not a lot of bumping. And the one question is, so if there's not a lot of bumping, does it really make sense doing a good job of it? Well, one signal that it might be is that after this incident happened, United joined Delta Airlines in offering an auction-based overbooking system. So you can see there's a headline. This is in September of 2017. United's going to let you quote, name your own price for giving up your seat. It's essentially an auction where people will say how much they would require to be paid to get off the flight. And the other thing that's of interest is that United had advertised, in fact, that they're willing to pay as much as $10,000. And that actually serves two purposes. On the one hand, it's advertising to people that, hey, they're really willing to pay, you name your price, they're willing to pay up to $10,000. That's a lot of money. So you shouldn't be too afraid of being bumped. The other is, of course, is it limits the compensation to $10,000. So imagine they don't have the risk of somebody demanding $100,000, and for some reason that's what they're going to end up having to pay. And again, we'll come back to this as well. So that's the motivation for the research that we're doing. And so the questions that we have, first of all, is how does accounting for demand endogeneity affect profit? Well, we have these preliminary numerical results that say that actually the revenue improvements can be large. In particular, if companies, if you set the price properly, right? If you set all three of those things properly, rather than just fooling with the booking limit, in some of our numerical examples, in reasonable ones, we're seeing something on the order of 5 to 10% average revenue increase. In some of the examples, it's much more so, but even in quite reasonable examples, it can be a lot. The next question would be, so is the auction scheme better than the fixed compensation scheme? And again, the answer is yes. Here, there are smaller, but still economically significant improvements. If you take an optimal fixed price scheme, which are the ones I'm talking about up here, and you compare auction-based schemes, the auction-based schemes do about 1 to 2% better in terms of average revenue than the analogous fixed price scheme. And 1 to 2% is something like an order of magnitude less than the initial benefit that you get, but 1 to 2% in revenue management is a lot of money. And so both of those things seem like they're worth doing. And finally, for bumping probabilities of about 0.1%, is taking bumping into account important? And the answer is yes. And we'll see if we have time for the numerical examples, those kinds of improvements that we're getting, the equilibrium outcome of the system is with bumping probabilities of 0.2%, 0.5%, not necessarily 0.1%, but it's still with very, very low bumping rates. And the way these problems are solved is really on a flight-by-flight basis. So some flights will have very high bumping probabilities, some will have fewer. For the flights where there's bumping, it's going to make a big difference. All right. In terms of the literature, there's, overbooking goes back a long, long time in operations research. But as I was saying before, that the classic way of approaching the problem is to assume that the demand distribution is exogenously defined. So there's tons and tons of work. These are some representative ones. But they're not taking the basic fact of demand endogeneity into account, which is what I want to do. Over the last 10 years, there have been some economics papers that specifically have looked at demand endogeneity, but they're highly, highly stylized. What they're doing is they're mechanism design papers. They're looking for optimal mechanisms, auction mechanisms. But for example, they don't include the possibility of setting booking limits. So it's purely price and auction mechanism design. And so at that level, it's stylized enough that it's actually not very useful operationally for the problem, where booking limits get used quite a bit. And finally, there's recent work on, quote, strategic customers in the operations management literature. These 3 papers down here look at variations of kinds of overbooking problems, but nothing that's really, again, realistic. This one by Alexandra from Le Riviere, that's on restaurant overbooking. The one by Cachon and Feldman is like a unit demand. Again, these are kind of, and also the one with Zhuan Ming, they're highly stylized. What we're going to do is we're going to actually go back to one of the first papers in the last 20 years that has been broadly cited on this notion of strategic customers, or quality of service dependent demand, by Jim Dana and Nick Petruzzi. And this is in a much simpler setting of just a news vendor problems, the simplest kind of inventory problem. We have an analogous situation, although it's a little more complex, because overbooking problems you'll see are doubly stochastic. And so they're a little more complicated to analyze. They're a little different. So that's the background. And now I want to get into the meat of the problem and define the model for you so you can see what's going on. I'll start out with model primitives. Maybe I'll stop for a moment because I've been burning through this stuff, because you know that I'm anxious to kind of get moving. But do people have questions? Are they confused about anything? I've got my chat box up, so you can either say I have a question and then I can respond to you, or you can just unmute yourself. Nope. Okay. I'm going to take that as an okay. So let me get into the model. So first of all, on the airline side, the airline, great, thank you. The airline has a flight, right? And that's going to take off, that it's selling tickets for, and the flight has K seats on it, right? And we're thinking, this is the simplest case. There's a lot of stuff that's homogeneous. Think of, it's all economy class seats. We're not worrying about different ticket classes and things like that. And if the airline bumps a customer, the airline's going to pay a rebooking cost that we call R. And the way to think about this is that if the airline bumps the customer, they're going to have to put that customer on another flight. If the flight that they put the customer on is another flight run by the same airline, and it's going to happen 5 minutes later and it's an empty flight, that rebooking cost probably is going to be something close to 0. On the other hand, imagine that the company's got to bump a customer, and in order to seat that customer on a plane, the company's going to have to buy a ticket from its competitor, right, to seat the bumped customer on the plane. Then that rebooking cost is going to be high, right? And so this is something essentially that's out of the airline's control, right? It's the kind of opportunity cost, or the marginal cost operationally of it having to bump a customer. Here are the airline's controls, and I color code controls in red. So it can charge a price for a ticket. It can set a booking limit that's going to be some number that's greater than or equal to K. And it can charge bumping compensation. And we're going to assume the ticket prices and the bumping compensations are non-negative. You know, there'll be a bunch of kind of basic assumptions about them. And the airline knows all of this stuff. And customers don't necessarily, so they know what the ticket price is, they know what the booking limit, they don't necessarily have to know what the booking limit is, but they know what the bumping compensation is, right? Customers also know this about themselves. So this is customers' individual valuations. They know what their own value of flying is. And in this paper, we're going to assume that everybody's got the same value of flying. Right, so you can imagine that's again a very restrictive assumption, but let's just say that the next paper is going to be where there's heterogeneous values of flying. Because what we want to do is we want to focus on what's called the hassle cost. That's the disutility of being bumped. Customers know their own value of flying. They know their own probability of not showing up for the flight, and they know their own hassle cost. That's their disutility of being bumped. The airline, because it's a common value of flying, the airline knows V. Because it's a common no-show probability, the airline also is able to estimate alpha, the no-show probability. The airline does not know individual customers' hassle costs. What they do know is they just know the distribution of the hassle costs. So imagine they've been, you know, they're collecting information, they've got a lot of experience. They can't really identify for any individual customer what his or her hassle cost is, but they know what the distribution is. And here are the two key distributions. The airline doesn't know exactly what demand is going to be. It's a random variable Q, but again, they've got a kind of distributional forecast. So they know what the demand distribution is. And again, they don't know what any given customer's hassle cost is, but they know there's a distribution in the population, and it has its own CDF. And the airline knows the two CDFs, but they don't know the individual realizations, right? In terms of the customer doesn't know and doesn't need to know what the CDFs of either of these things are. Okay. Any questions about the basic setup? These are the primitive data, and now we're going to put, you know, describe some kind of interaction of what goes on and talk about equations that describe the trade-offs. All right. So what we're going to do is the next thing that I'm going to do is I'm going to define what the equilibrium is, just so you understand. And like any equilibrium, there are at least two sides of it. So I'm going to describe one side of it, and that is, suppose the customers are going to know what the equilibrium bumping probability is. So, and think of it as the customers know, they look at the BTS reports, they know that, you know, that the bumping probability is 1/10 of 1% or 1% or whatever the number is, right? And so they have some estimate of what the equilibrium bumping probability is. And based on that, and knowing what the price is, and knowing their own value of flying, what their own no-show probability is, they can, and all these data, they can calculate what their expected value is of buying a ticket. So they buy a ticket at price P. The expected value of flying for them is the probability that they show up times the value that they get when they actually fly. And the expected value of being bumped is the probability that they show up, and then the conditional probability that they get bumped, given that they're on the flight. And given that they show up and they're bumped, then they get some bumping compensation, but they lose the hassle cost, right? That's their disutility. And so this is the expected value for them, right, of buying a ticket, right? And then what we can do is we can find out, you can see that actually the expected value is going to be decreasing in W. So we can find a W hat, that's a threshold W, so that for the break-even expected utility. So that is any customer with a W that's less than or equal to W hat is going to have an expected value of buying the ticket that's non-negative. and any value that has a W that's strictly greater than W hat has a negative expected value, right? And it's not going to buy a ticket. So this W hat is going to feed back in to this hassle cost distribution, and it's going to thin the demand. And that's how the Dane and Petruzzi model works, and a lot of the models in these literature. So it's really a fraction. We're not going to take some kind of binomial distribution. We're going to have a lot of other distributions in here. All right. So so that's half. You start with a beta and you end up with a W hat. Now the next thing we want to do is we want to start with W hat to complete the equilibrium calculation. We want to start with W hat and end up with beta. Right. So again, given an equilibrium threshold hassle cost W hat, we can define the sales. That's the minimum of the booking limit, right? The airline will never sell more than B tickets if B is the booking limit, and what the demand is. And the demand is just the random raw demand that's been thinned by the fraction of customers who have a hassle cost that's less than or equal to that threshold hassle cost, right? So the idea is that the higher W hat, the larger the demand distribution, the lower W hat, the smaller the demand distribution. And this is exactly what the endogenous demand function looks like, right? Very simple. Given, and notice that sales is some random variable because it's based on this random variable here. Given some random number of sales, so the actual number of people who show up is actually a doubly stochastic random variable, right? For some fixed little s, there's going to be a random number of people who show up. The simplest function would be like a binomial distribution, right? If everybody has a probability of 1 minus alpha, every ticket that's sold has a probability of 1 minus alpha of showing up, then we'll have a binomial distribution. But then there's a second level of randomness in that the sales themselves is random, right? And that's not such a problem here, right? That's easy. We can condition and calculate. So I could, well, I'll do that in a moment. This is not such a problem. It's a little trickier here. The number of bump passengers is again, the number of tickets sold, or the number who show up, I should say, minus the capacity of the plane. So if the number who show up is less than K, then nobody gets bumped, right? And the plane flies with empty seats. If the number who show up is strictly greater than K, they're going to have to bump N minus K passengers, right? And they're going to have to pay those people bumping compensation, right? And finally, once we have the number of customers who show up and the number of bump passengers, we can calculate the statistic that we're going to use for the bumping probability, right? So that's just the expected number of people who get bumped divided by the expected number of people who show up. And notice that this actually is a kind of, this is an analog of that Bureau of Transportation statistic of the 0.1%. For those of you who are familiar with these kinds of models, for example, in the Dane and Petruzzi model, they use something that's slightly different. It's called the ex-ante bumping probability. So buying a ticket, I know for me, myself, what's my personal probability of being bumped. Whereas this is really like the fraction of customers who are bumped. And they can be a little different. When the numbers are so low, they're not very different. But I want to point out that the way we're doing it, it's not strictly speaking what you would call, an economist would call a rational expectations equilibrium. Rational expectations would have the ex-ante bumping probability. And if I have time at the end, we can talk a little bit. It turns out actually that the ex-ante, you can put it in there. It's not very well behaved actually. And so this actually, also I think practically speaking, it makes more sense that people hear about these bumping probabilities on a given flight. You don't really have a lot of experience that you're going to learn, right? What the ex-ante bumping probability is going to be. All right. So that's the second half. You start with W hat and you end up with beta, the bumping probability. So now we've got, you start with beta, you end up with W hat, you start with W hat, you end up with beta, and that's an equilibrium. All right, so that's the full problem. Here's the full problem. The airline's going to set a price P, a booking limit B, bumping compensation C to maximize the expected profit. where the expected profit is just the expectation of the price times the number of tickets sold, minus the bumping compensation times plus the rebooking cost per passenger that's bumped, times the number of passengers who are bumped, right? Subject to, it's essentially this customer equilibrium constraint where then we've got a bunch of definitions. We've got a definition of beta. We could just plug that in there, right? And we've got a definition of the number of shows that goes into these two parts of beta. We could plug that in there. And we've got the definition of the number of tickets sold, which goes in here. So you could do a bunch of substitutions and end up with one big kind of nasty equilibrium equation. And just so it's a little easier on the eyes, I've split it up. So that's a problem we're going to solve. Are there questions about this? Because we're going to come back. We're going to solve this about, kind of, as they say, every which way but Tuesday or Monday or Wednesday. I forget what day of the week that expression is. All right. So before we get there, I forgot. I want to point out. So how are we going to calculate the bumping probability? That's actually a little bit tricky. So again, we're going to start out with sales. That's a function of the booking limit and the equilibrium break-even hassle cost. The denominator, the expected number of customers who actually show up, is it's doubly stochastic. But if you first condition on little s and take the conditional expectation, each of the little s customers is going to have an expected probability of showing up of 1 minus alpha, and then we'll just uncondition and take the expectation of the number of tickets sold. We can do the same kind of conditioning for the expected number of bump customers, where I'll take a double. You can see I'm conditioning here. The inside expectation is for some fixed little s. This is a harder thing to analyze, though. But the nice thing is that this conditional expectation is essentially, it's a loss function that's directly analogous to the loss functions in inventory theory. And what I'm going to do is I'm going to define a loss function. I'm going to call it little L, which for a given number of tickets sold will calculate the expected number of lost customers for a given number of tickets sold. And then again, I can uncondition and take the expectation. And when I go to differentiate, this is a function that I know I can do something with. And also, in the paper, we have a very general definition. And here's the definition. The loss function is just convex increasing with a couple of properties, right? So on the horizontal axis is the number of tickets sold. On the vertical axis is the conditional expectation of the number of lost bumped customers given that number of tickets sold. If the number of tickets sold is less than or equal to the booking limit, then the expected number of lost customers ought to be 0. And as you increase S, it's convex increasing. And it's asymptotically the derivative of the loss function, the rate at which the expected number of customers lost, is increasing at the probability of a customer showing up. Because unlike in inventory theory, at a certain point, every unit ordered that you don't have stock for is lost. So the loss function increases at rate 1. Here, every ticket I sell, there's still only a 0.9 or 1 minus alpha chance that customer shows up. So the asymptote's a little different. And this is really all we need for the loss function. So for example, it could be that no-show probabilities, even though they're show probabilities, even though they're marginally 1 minus alpha, they could be correlated with each other, and that would affect the loss function, and that's not a problem. Okay, so here's again the full problem that's a little bit simplified. So the airline's gonna set the price, the booking limit, the bumping compensation to maximize expected profit. Here, it's the price per ticket times the expected number of tickets sold, minus the bumping compensation and rebooking cost times the expected number of lost customers, subject to, again, that customer equilibrium, and subject to the definition of the bumping probability and the definition of sales. And I'm assuming that this loss function itself is defined somewhere or other that I haven't talked about it explicitly, and I won't. All right, any questions? So this is what we're going to analyze over and over again. Good. All right. So first thing we're going to do is the traditional analysis. Where we're going to optimize just the booking limit. So here's the problem. Rather than maximizing over the price, the booking limit, and the bumping compensation, we're taking the price and the booking limit as exogenously defined. And rather than taking the demand as being an endogenous result, an equilibrium result of the quality of service, we're going to say that there's some threshold probability and the threshold hassle cost that the airline's going to take also as exogenously defined. And in general, the idea is that the airline just sees Q times G of W hat, and this whole thing, this whole quantity together is the demand distribution that the airline sees, and the airline's not even thinking that the demand's being thinned at all. But given that the W hat is exogenously defined, there is no equilibrium equation. So this is it. There are no constraints. And we can just differentiate this thing. And this is the traditional OR, a continuous version of the traditional OR analysis. So we'll take the derivative with respect to B. Here are the first order conditions. And you can see here, so it's the price times the tail probability minus the bumping cost times you can see the marginal, right? This is kind of the first derivative of the expected loss times the bumping probability, that, or the tail probability, that factors out. And you can see that we end up with a simple first order equation that we can invert, where the optimal booking limit is just the inverse of the derivative of the loss function. And this is the critical fractile. So you can see, because the problem's doubly stochastic, rather than like in an inventory problem, it'd be the inverse of the demand function. Here it's the inverse of the analog of the demand function is kind of the loss function. So it's the inverse of the loss function. But that completely characterizes the booking limit. And I'm going to say that it's B star of M for myopic, because it's myopically not taking into account the fact that demand is endogenous. So that's kind of our baseline. The next thing that we can do is we can go back and say, okay, so again, starting with the basic problem, but now saying that demand's actually endogenous, what happens if we go to solve this whole thing? And now, again, we essentially have got this one equilibrium constraint. So when we go to differentiate the objective function with respect to B, we get this second term, right, from the chain rule. And the first term is just the direct derivative of the objective function with respect to B. And the second term is the indirect effect of the equilibrium constraint. And the tricky thing here is characterizing how the equilibrium threshold hassle cost changes with the booking limit, right? But in fact, and it's a kind of a nasty thing. It's difficult to characterize, but we, after kind of mushing things around for a long time, and I have to say, Rowena probably had a deep migraine headache for many months looking at this thing. That she figured out that there's this condition that if the bumping probability is greater than this quantity, that it looks like kind of it's like a Mills ratio, or kind of like an inverse hazard rate. If the bumping this equilibrium quantity is greater than this function of another equilibrium quantity, and it holds for all potential booking limits. So the equilibrium just defined by all potential booking limits, if that holds, then what we call the strategic booking limit, which takes into account endogenous demand, will be strictly less than the myopic booking limit. So this would be the intuitive result. It's not particularly satisfying because it's based on these equilibrium quantities. But we can say two things, one of which is pretty interesting. The first thing that we can say is that actually if the hassle cost distribution is decreasing failure rate, then actually this condition holds for all B. And then it's always true that the that the strategic booking limit's going to be strictly less than the myopic one. Now, the problem is that a decreasing failure rate hassle cost distribution would mean that it's at a certain level kind of heavy-tailed, right? And I don't know really how much that would happen, but this is sufficient. There may be other conditions under which it holds. More interesting is if you look at the right-hand side of that inequality for the sufficient condition, you can see that as the price gets very close to the expected value of the ticket, right? That is the probability of showing up and then the expected value of flying, given that you show up. As the price gets very close to it, the right-hand side goes to 0. And if there's any kind of bumping, which is the only interesting case that we care about, then the condition is going to be trivially satisfied. And that leads us to think that this could be an interesting case if we can make something of it. And that's what I'm going to talk about next. Any question about where we are? I think the next part is more, is the part that I really, I like it more and more as we go along in the talk. It's my own personal preference, but let's keep going. All right. So those are two cases where we're just, the booking limit is our only control. And we've compared the optimal booking limit where we assume that demand is exogenously defined to the optimal booking limit where we're taking demand endogeneity into account. All right. Next, we're going to look at all three controls. So again, we're back to this main version of our problem. The airline's going to choose the price, the booking limit, the bumping compensation to maximize the expected profit subject to this customer equilibrium condition and subject to these definitional constraints. And what we're going to do is we're going to see that we can actually reduce the problem by using that condition that was hinted at in the simpler version of the problem. In particular, we're able to show that given any policy, so imagine an airline sets a price, some arbitrary price, sets some, well, the price, we're restricting prices to be less than or equal to the expected value of flying. So given any price between 0 and 1 minus alpha v, giving any booking limit greater than or equal to k, and giving any bumping cost that's greater than or equal to 0, if that triple obtains an actual equilibrium, then we can find, we can actually set the price to equal the expected value of flying and obtain an equilibrium that obtains the same equilibrium with the same expected profits. And in particular, and to do that, we're going to have to change the bumping compensation as well. Those two, in a certain sense, are complements for each other. And we're going to trade one off for the other. In particular, that means that if there is an optimal policy, then there's going to exist one where we can set the price to be exactly equal to the expected value of flying. And this is really, really nice for a couple of reasons. First of all, it's going to eliminate price as one of the optimization variables because we know that there's right? We don't need to use price as a control because we're just going to set it to equal 1 minus alpha v to begin with. The other thing that's really nice is that if we set price to equal 1 minus alpha v, the equilibrium condition simplifies, right? Here's the new equilibrium condition. And notice 1 minus alpha is strictly positive. And the interesting case is when there's bumping, so that will be strictly positive. And in that case where there's actually some bumping going on, then you can see that that the bumping compensation uniquely determines the equilibrium threshold hassle cost. So and what's happening is the problem's decoupling. We're using the price to suck up the expected value of flying, and managing bumping and the compensation of bumping and the demand distribution completely falls on C and B. And so that the problem decouples in that very nice way. The last thing I'll point out that's very nice is that notice that if the equilibrium hassle cost W hat equals C, that means that anybody who has a W that's less than W hat is going to be happy to be bumped. because the C is going to be greater than their W. And anybody with a hassle cost that's above W hat, a W greater than W hat, is not going to buy a ticket in the first place, because that has to do with the demand thinning. So what we end up with is an easier to analyze problem that actually, by the nature of the equilibrium, we don't have to worry about kind of long-term customer ill will, right? And so these are the two things I was talking about, right? I set a bumping compensation that tells me exactly what the equilibrium hassle cost is, and I can actually now just substitute the bumping compensation into the sales distribution, and we can see exactly how the bumping compensation directly affects the demand distribution. So at a certain level, demand is still endogenously defined because it's a function of our C, but it's not endogenous in that it's not an equilibrium outcome, right? Before we had this objective function subject to equilibrium constraints, and now we don't need the equilibrium constraints because that S is completely defined by B and C, and we don't have to worry about W hat being part of the definition of S. So now that we've got this new objective function, we can differentiate it the way we did with the original problem, right? And so we're back in the world where we've got this myopic optimization problem, and we get our first result for the broader problem with three different controls. First of all, if there exists an optimal policy, we saw that there exists an optimal policy that sets the strategic price to equal the expected value of flying. And given that the price equals the expected value of flying, for any candidate bumping compensation, we can solve that myopic, the original myopic booking limit problem to figure out the optimal strategic booking limit, right? Originally, we had P up here, but we know that P equals 1 minus alpha V. So the only thing that's varying here is C. And so finally, we can figure out the entire optimal overbooking policy through a line search on C, where what we're searching over actually is this closed form solution. So it's a very, very simple problem to solve. One last thing I'll say is that, you know, you might be thinking, so there's an infinite set of prices that can be optimal. We're choosing one of them. At a certain level, that means the problem is underdetermined, right? Where we've got many optimal solutions. And what that means really is, I think it's partly because we don't have a distribution on V. There's no heterogeneity. But I think for a first analysis, where we're taking into account the heterogeneity of the hassle cost distribution, it's providing us some nice insight that at least one way of thinking of the problem, even if in more complex cases that it's not optimal to do it, you can try to decouple the value of flying from the bumping compensation that you offer. Whereas if you make sure to set the price so that you can it's kind of a fair deal on the value of flying, then you can control demand and customer satisfaction directly with the bumping compensation. So that's the next result. The last result that I want to talk about, and we've got about 10 minutes left, that's good, is auction-based bumping compensation. And so the overall story is, rather than fixed bumping compensation, if the airline has to bump customers, they're going to run an auction. The way I noted that Delta or United runs an auction, but it's more complicated to evaluate because for any individual customer, first of all, whether or not they get bumped is going to depend on what they bid in the auction, which is going to depend on their private hassle costs. And same thing, what the bumping compensation is going to depend on their auction bid, which is going to, right, it's going to depend on the number of customers who have to be bumped, their private W, and these outcomes of the auction. So it can be very, very complicated. In this paper, we're not really looking for optimal auction mechanisms. So we're just going to use a kind of off-the-shelf auction mechanism that we know behaves well, that will indicate how that it's actually we're going to use a uniform price auction, but a Vickrey Gross Clark auction would do a similar kind of thing. It's easy to analyze. And here's how the uniform price auction works. Suppose that the airline has to bump customers. So N customers show up, and N is strictly greater than K, the capacity of the flight. What the airline's going to do is it's going to ask each passenger to bid some quantity omega, right, that we want omega, so it looks kind of like a W, but it's not, that he or she wishes to be paid if bumped, right? So the idea is that I may say, so you guys have PhDs. I mean, in another world where people are actually flying, in people, like when I was a PhD student, I was super happy to get bumped, right? Because I'd get a voucher or a little bit of money. If now that I'm older and stodgier, I'm less happy to get bumped. And so you can imagine that there's going to be some heterogeneity in those bumping costs. And what the airline's going to do is going to order the bids from smallest to largest. So this is just the notation of order statistics, right? That's the smallest bid. The second smallest, that's the largest bid. And what the airline's going to do is it's going to take those N minus K customers that it has to bump, and it's going to offer them as bumping compensation the bid of the N minus K plus first customer. So that would be the last customer to stay on the flight. That's the lowest bid for somebody who still stays on the flight. Notice that this is greater than or equal to the bids of any of the customers who gets bumped. So that's good. So here's our main result for auctions. Suppose that we've got a price, again, it's somewhere between 0 and the expected value of flying. I don't know what it is, but let's just say we have a price like that. Then it's optimal for passengers to bid their hassle costs, right? So we get this kind of incentive compatibility result, and that's a result. It's easy to prove, but it just comes right out of the format of the uniform price auction with single unit demand. And customers are happy to be bumped, right? Because we know that what they're going to get paid, the WN minus K plus 1 bid, is going to be bigger than any of the first of the up to K, right, up to K bidders. So they're all going to be happy to be bumped. And what that means, if they're all happy to be bumped, everybody's going to be willing to buy a ticket. So if you get bumped, you're going to be happy to be bumped. Everybody's willing to buy a ticket. This is the maximum demand that you can get. And given that it doesn't depend on the price at all, because people are happy to be bumped. So if they're happy to be bumped, you might as well charge the complete expected value of flying. So the optimal auction price actually is what we had in the fixed compensation scheme as well. And again, so we know what the optimal price is. The compensation is auction dependent, but in terms of before the flight, what the airline has to figure out is the booking limit. And again, we've got a one-dimensional search. This search is a lot more complicated, though, because it depends on the outcome of auctions as you increase the booking limit, right? And so you've got to do a lot of analysis of order statistics to characterize it, right? So that's the auction scheme. And you can see there's a lot of analogs between the optimal fixed compensation scheme and the optimal auction scheme. The price is the expected value of flying. Customers are happy to be bumped, and we're back to a kind of one-dimensional problem. Now, one thing I want to point out is that these airlines offer caps on their auction. You may remember from the very beginning of the talk, I showed that newspaper article where it said United is offering a name your own price to be bumped system, and they're willing to pay up to $10,000. And that $10,000 is like a cap on the auction. And if we use a capped auction, I can't compare the original auction to the fixed compensation scheme analytically. I can compare it numerically, but I can compare a capped auction directly to the fixed compensation scheme. So I want to do that next. So again, keep in the back of your mind that the airline upfront advertises a maximum payment that is quite generous, but it's still a maximum that they're going to pay. And we're going to analyze a scheme again where the airline's setting the price equal to the expected value of flying. In the cap scheme, it's not necessarily optimal. So this might not be the optimal capped auction scheme, but I can analyze it directly. So imagine we start out with some fixed compensation scheme where the price equals the expected value of flying, and there's some arbitrary booking limit, and there's some arbitrary bumping compensation. So I know that this is price for the fixed scheme, the price is optimal. These may or may not be optimal. But given this triple, we can construct an auction-based scheme, right, where the auction price is the same as the fixed compensation price. The booking limit for the auction, an auction-based flight, is the same as the booking limit for the fixed compensation scheme. And the cap, that $10,000, is the same as the fixed compensation it's the same as the fixed compensation, bumping compensation in the fixed compensation scheme. So we can match the parameters, and then we can show that those two schemes have exactly the same W hat, right? Because let me put it this way, if the airline is setting, in the auction scheme, if the airline's setting the price to equal the expected value of flying, a customer is only going to buy a ticket if the cap is greater than or equal to his or her private W, right? And that's exactly what we get here, right? The fixed compensation equals W hat, and here the auction compensation also equals W hat, right? So they've got the same W hat. That means that they're going to have the same expected revenues and rerouting costs. But given, let's say that there's a non-zero density for the hassle cost distribution, then the auction scheme is going to have a strictly lower expected bumping cost. So they're going to have the same expected revenues, the same expected rerouting costs, but the auction scheme is going to have a strictly lower expected bumping cost, and that's because the airline gets to rank the hassle costs from lowest to highest and only pick the n-k lowest ones, right? So it gets the extra information. It's collecting that rent from customers. In the fixed compensation scheme, the airline doesn't know what the hassle costs are. And so the auction scheme, this capped auction scheme, earns strictly higher expected profits, and it holds for the optimal fixed compensation scheme. So theoretically, that's pretty much everything. The only thing I'd say is that while for a capped auction, the price equaling the expected value of flying is not necessarily optimal. We found conditions where, in fact, it is optimal. Conditions under which you would never have the cap. The cap would be infinity, and when the cap's infinity, it's an uncapped auction. And so we end up with the original problem. Now, I realize that I'm out of time. I'm happy to spend another 5 minutes just flashing you the numerical results for people who want to hang around. For people who have to leave, I surely won't be offended at all, because I know that I'm running overtime here. So let me just show you. The last thing I'll show you are numerical examples of the performance differences. The first thing I want to show you is back to the very first problem, which is suppose that there's a price and a bumping compensation that are not optimized. There just happen to be a price and a bumping compensation. They may seem reasonable. And what the airline's going to do is it's going to set a booking limit. And what we're going to do is we're going to compare outcomes of when the airline sets the booking limit myopically to the outcome where the airline sets the booking limit strategically. I want to point out, and I probably should have had more slides here, but I want to point out that when the airline sets the booking limit myopically, customers are still strategic. So what's going to happen is the airline will end up in some equilibrium, and that's the demand distribution the airline thinks it gets. And so we'll find a W hat that's consistent, but the airline is not taking that W hat into account. So we've got 720 examples. So you'll see this is like a first order numerical analysis where we just try out, we try out 5 different values and we try out 5 different margins, the difference between P and the expected value of flying. And we try out 3 different bumping, no-show probabilities, 5%, 10%, 20%, and so on and so forth. So we've got a big grid of examples that we're testing. For each of the 720 examples, we're going to find the optimal myopic booking limit and the optimal strategic booking limit. And all the other, once we have those, we can calculate all the relevant statistics. For each of the statistics, we'll calculate the ratio of the myopic outcome to the strategic outcome. So we can see how the 2 of them compare. And finally, we'll sort them from smallest to largest. And so what I'll be doing is reporting distributional summary statistics for the distribution of each of the ratios across all 107 examples. So for example, we have 720 examples. And here is I'm comparing the ratio of the strategic booking limit to the actual capacity of the flight. So you can see the smallest that the strategic booking limit ever is exactly equal to K. The median is about 8% more than K. And those are for cases like a plane size of 50 or 100 or 200 or 400, I think are the 4 cases that we have. The mean you can see is about the booking limit's about 10% more, and the maximum over all 720 examples is 28% more. So just to give you an understanding of how these things work, we can calculate, rather than the strategic booking limit divided by the size of the plane, we could calculate the myopic booking limit divided by the strategic booking limit. In our examples, even though I think everything is pretty much normally distributed, so we don't have kind of heavier tail distributions, the strategic booking limit's always smaller than the myopic booking limit. So they're the same sometimes, especially when they both equal K. But you can see that the myopic booking limit is quite a bit higher than the strategic booking limit, right? So here it would be 16% rather than 10%, for example, in terms of averages. These are the equilibrium bumping probabilities for the strategic booking limits. Here you can see the median and the mean is 0.2%, 0.3%. So it's a little higher than 0.1%, but it's in the ballpark. And that's not unreasonable. And the myopic bumping probabilities are much higher. The reason that I think that we have that ratio, well, one thing is that the max is infinite when, imagine that the bumping probability for the strategic booking limit is 0, and it's non-zero for the strategic booking limit. We're going to get infinity there, so we don't get a mean. And finally, in terms of profits, you can see that the average profit increase is about 27%. Now, my guess is that, again, this is a very broad set of examples. To have a better sense within the subset that are realistic examples, it's probably not going to be 27%, but my guess is it could be 5 to 10%, somewhere in that range. Here's a similar example where we're comparing the optimal fixed compensation scheme, so where we optimize over the price and the booking limit and the bumping compensation, to the analogous optimal auction scheme, but it's not a capped auction, so it's an auction without a cap. We've got 360 examples, and we've got the same, right? We've got the same drill. So we calculate a bunch of ratios. Here's the ratio of the optimal fixed bumping compensation to the expected compensation from the auction scheme. So you can see here, the auction does exactly, for those of you who are familiar with auctions, it's not surprising at all. The auction, there's price discrimination that's going on. The optimal auction scheme is going to, on average, do better than the fixed compensation scheme, given the setup. You can see that here's we get similar statistics for for these 360 examples. The median and the mean excess booking is a little bit higher. And you can see that with the auction scheme, it increases the booking limits a little bit. Again, in the strategic case, they're a little higher, but they're still under 0.5%. And it's interesting that from the auction scheme, even though the booking limits are just a little bit higher, the amount of bumping is so low that the bumping probability goes up quite a bit. And again, we earn a little bit more, 1 to 2% extra on average. So again, it's in a certain sense, it's an order of magnitude less improvement, but a 1 to 2% improvement in revenue management system that goes straight to the bottom line. And so that's a big deal. So that's pretty much it. I'm sorry I ran over. So given if we take the price and the bumping compensation as fixed, we saw that strategic booking limits can greatly outperform myopic ones, but they're tricky to calculate. If we open it up and control the price and the bumping compensation and the booking limit, then we see that there's an optimal policy that sets the price equal to the expected value of flying, and that the expected cost of being bumped decouples from the price, and that allows the airline to cover all bump customers' hassle costs, right? So customers are happy, the airline makes more money, and it's easier to understand what's going on. The auction scheme has the same kind of decoupling that goes on, right? Decoupling the value of flying from the cost of being bumped. It has the same ability to cover all bump customers' hassle costs. It's got lower hassle costs, right? It's doing price discrimination. It's able to skim off the lowest of the hassle costs when it bumps customers, and so that adds 1 to 2% on adds a couple percent to the revenues. One last thing, I don't write it here, but another nice thing for those of you who know about auctions is it's a price discovery mechanism. So the airlines who run these auctions, they're getting to see what people say their hassle costs are, and that lets them estimate the hassle cost distribution, right? Which is, I think, interesting and important in its own right. So that's pretty much it. If anybody has questions at the end, I know I've run over by almost 10 minutes, and I thank you for your patience.
Thank you, Noah, for this really excellent talk. And I will start actually with some questions. Sure. That you mentioned that really important notion of the magnitude that you showed that basically the study of this mechanism, despite of the small percentages, can actually be very beneficial in terms of the revenue. And my question is that in general, that the airline companies that for different flights, even for within the same flight on a particular day, they can dynamically adjust their book limit by observing the customers who have so far booked their tickets. And technically, they can also look into the customers' historical records to actually analyze, for example, the no-show probability for each customer, all of this private information. So my question actually is twofold. One is that what kind of magnitude do you think this more dynamic and information mining type of strategies can improve the profit? And second is that, do you think this is a privacy issue around this?
Yeah, that's a good question. I don't think it's a privacy issue because it's revealed behavior. So if people are filling out auction information, the fact that they're doing so, so it is a privacy issue. My guess is legally it's probably not a privacy issue, that it's already covered when somebody clicks something to say that I'm buying this ticket and I want to fly, and therefore you can have all the data back to the day I was born, kind of thing. It's probably covered in those kinds of clauses. In terms of how much more it can buy you, my guess is that it probably can buy you something. It's already a pretty complicated problem, but it would, in theory, it'd be of interest to look at, right? I think Jerry, in particular, Jerry comes originally from a background in the airline industry, and he has people who he knows, and we've tried talking with airlines because it would be so. Especially in the auction side, I think it'd be interesting to try to calibrate our model a little better, just to see a little more practically what the benefits would be. And also, it may, to the extent it would help us to validate or invalidate this notion of setting the price, if not exactly equal to some expected value of flying, something close to it. But you know, I'm just making it up. So, but my gut instinct, which is probably not worth a lot, is that it's, you know, it's probably worth looking at. Although I would do the easier stuff first, right?
Sure, of course. Yeah. Thank you.
Yeah, I have a question. Just thinking about like a multi-class model, and I wonder if you had the business travelers willing to pay more for being able to change and blah blah blah, and
Yeah.
maybe had the bumping as part of a feature of that ticket. So the business class would pay more to know they would not be bumped, and they just wouldn't be
Yeah.
that hassle. And then the cheap ones, you'd tell them up front, okay, well, it could happen. We'll pay you $100, whatever. And
Right.
people
That is
buy those. And
yeah, no, exactly. So that's a great idea. I think practically speaking, that's kind of what happens. I think business class so first of all, with an auction, it doesn't matter. Business class customers say, well, you got to pay me $10,000.
yeah, no, but I'm thinking for the airline, this could help them drive up the price for the business class or whatever. So you know, don't buy the business class, you will face this possibility of being bumped for $100 or whatever. And
right.
So
Yeah, for sure. So how it would play out in a kind of nested scheme, I don't know. But surely, even within economy class, right, they're going to be, I'm sure that there's some heterogeneity. So I mean, we've thought about, so how is the value that somebody gets from flying related to the implicit disutility of being bumped? And I'm sure that there's some kind of relationship, that there's probably positive correlation, but my guess is that it's not perfect. You know, it really depends on circumstance, right? Where you may be going on vacation and you're a leisure traveler, you've actually have a fairly low disutility of being bumped, or low value of the ticket, and you're willing to buy it far in advance, and you're willing to do a bunch of different things. On the other hand, for this trip, you're going to take a cruise or something, and if you miss the flight, you're going to miss the cruise ship. And so there, right, the disutility of being bumped is going to be much higher than what you would think otherwise. And so that's a kind of first order extension. It's more than an extension. I think it's, you know, we'll probably have to use copulas or something like that, right, to get some kind of general, because now it's a two-dimensional distribution, right, of the value of flying and the hassle cost distribution. But that would be a general way. There could be special cases where, you know, they're perfectly correlated, they're completely independent, and you analyze those extremes. And then another one would be across classes. My understanding of what the airlines do now, and I don't really know that well. So imagine I talk to colleagues, you know, like you, who have particular expertise. I say, so how do the airlines do it? Or sometimes I will actually talk to OR, you know, people in OR at airlines. And my understanding is that, you know, they do very simple stuff. Often they take averages across classes. You know, it's just so much data. But I think all those things, you know, I don't know. I think technically they're really interesting questions. Practically speaking, getting back to Jay's question, I imagine that it would be worthwhile. But, you know, frankly, I have no idea.
Okay. Yeah, I was just kind of thinking a little bit about some of this literature in more queuing, where if you have multiple classes, you may want to sort of force delay, idleness, whatever, for a lower class to make it more painful for the people willing to pay the higher price for not having that delay. And so I'm thinking, you know, there might be some trade-off there with the pain of getting bumped and getting
right, yeah,
might make me willing to pay all that much more for the first
class. So I would group that in a kind of, you might call them adverse selection problems, so you've got different classes, And there are pooling equilibria where everybody gets the same treatment versus separating equilibria.
Right.
Yeah, and those are tricky to deal with. But that makes sense to me. Anybody else? Great.
Right.
Well, thank you so much. I had a great day, even though it's kind of a virtual day. It was great. I really enjoyed talking to everybody. Thank you for being patient with me through the talk.
Thank you so much, Noah, for virtually visiting us and giving.
Thank you.
Thank you
Yes.
so much.
Thanks.
Nice talk.
Thanks. Yep. Thank you.
Thank
Have a
you.
good night. Have a good week.
Yeah,
Bye-bye.
you-
Bye-bye,
Bye.
everybody.